Hello everyone, welcome to today's lesson. What we're going to look at today is how can we graphically represent a complex number um, on a set of axes. You will recall that typically with a set of axes, the horizontal axis is referred to as the x, the independent axis. The vertical axis we refer to as the y-axis, which is the dependent axis. Well, if you're going to graph a complex number in rectangular form on a set of axes, we have to change things slightly. So what we do is we call the horizontal axis the real axis. The real part, remember, of a complex number in rectangular form, that is your a, the a plus b times j. And we refer to the vertical axis as the imaginary axis. So what would happen there is whatever the letter b is, whatever the number b is in front of the j multiplied by the j, that's what we would graph on the imaginary axis. So let's have a look at some examples here. It's actually relatively straightforward. This is not a difficult topic, but it will become important later on when we get into other forms of complex numbers, knowing how to graph them. So here's example number one. It's asking us to graph the complex number 2 plus 4j. Now you can clearly see that 2 is the real part, so that is your a. The number in front, the coefficient of the j is positive 4, that's your b. Well, how would we graph that on the real and imaginary plane? Well, we go along 2 on the real axis over to here, just like it's basically the same thing as if you were plotting the point 2 comma 4. That's what it's like. 2 on the real axis, 4 on the imaginary axis, and that's up to there. So basically we have a point right there. That's where the point would be located. Now something else that you have to add to the graph is a vector from the origin 0, 0 up to that point. So it would look something like this. Now I don't have a straight edge with me here now, but hopefully you have a straight edge. Make sure you use a ruler or some kind of a straight edge when you're graphing these. So here is the number 2 plus 4j. That's how we graph it. You'll notice that this number ends up in quadrant number 1. But depending on the signs of the a and the b, it's possible that your complex number could end up in any of the 4 quadrants. In fact, if a or b is equal to 0, what will happen is your complex number will actually lie right on top of either the real or the imaginary axes. And we'll see some examples of that in just a little while. So graphing a complex number using a real and imaginary axis is not difficult at all. There's another example here on the top of page 9. I'll have a look at this one as well. We're graphing the number -3 subtract 2j. You can clearly see it's in rectangular form. The real part is -3, and the imaginary part is -2j. So what we do is from the origin, again, we go -3 on the real, so that's 3 to the left. And then because we have -2 in front of the j, we go down 2 blocks, and there is the point that we end up with right there. And of course, again, we draw a vector from the origin to that point. Don't forget to draw an arrow on the end of the vector. So here is the number -3 subtract 2j. So it's not a difficult topic whatsoever to actually graph a complex number in rectangular form. Notice that this number ends up in quadrant number 3. Of course, in case you forget, remember how we number these 4 quadrants: quadrant number 1, quadrant number 2, quadrant number 3, and quadrant number 4. That's how the quadrants are all numbered. Okay. Now there's some practice questions after that. On the bottom of page 9. You can just try these on your own. All the solutions have been posted in D2L, so make sure you have a look at those and just practice graphing them. And the other thing I'd like to cover in this video is on page 10, if you know how to graph one complex number, you can actually use that technique to graph the sum of 2 complex numbers, or even their difference. So here's example number 6. This technique is called the tip-to-tail method. All right, and I'll explain exactly what that means when we do some examples right here. So part A says find the sum of 1 plus 2j, 1 plus 2j, plus, sum of course means add, 3 plus j. All right, so how can we use graphing to find the sum of two complex numbers in rectangular form? Well, we start off by plotting the first number as a vector, 1 plus 2j. So we would go 1 to the right and 2 up. There is 1 plus 2j right there as a complex number. That's the way we would graph it. Now, we're also going to graph 3 plus j, but we do not start at the origin. In fact, we start the second complex number where the first complex number ended off. In other words, at the head of the vector. So 3 would ordinarily mean go 3 to the right from the origin, but now we go 3 to the right from the vector that we ended off with. So 1, 2, 3 to the right, and plus 1j would mean 1 up. So I go up 1, and there is the point where the second vector ends off. I draw another vector, hopefully using a straight edge, to that point. And now you just read off from the graph what is that complex number. Well, you can clearly see that 4 on the real part, 3 on the imaginary part. So that would become 4 plus 3j. Now, obviously, this is not the most efficient way to add or to subtract complex numbers in rectangular form. If you were asked to just add two complex numbers, you would not be expected to do it this way unless the question clearly said to use this technique. All right, so let's have a look at, there's one more example I'd like to have a look at with you, and this is on the bottom of page 10. This is saying find the sum of, well, actually it's not a sum, is it? This is actually a difference. You can see that it's a subtraction here. Well, what you should do if you're subtracting two complex numbers, and if you want to use this method, you should change it to an addition. So the first thing to do would be to call this 5 minus 2j plus, and now for the second complex number, you actually take its opposite, which means you change the signs of all the terms that are inside. So negative 2 minus j. So if you're going to use this technique to subtract two complex numbers, that's what you have to do first. But as soon as you do that, then the technique is relatively straightforward. So let's graph the first complex number, 5 plus 2j. So from the origin, I go 5 to the right on the real axis and 2 down. So we end up at this point right there. Draw your vector. Draw it straighter than I'm drawing it. Draw your vector, your resultant vector. Here's your number. And now from that point where we left off, we're going to go 2 to the left, because that's where the real is. The real, remember, is your horizontal movement. So 2 to the left over to here, and 1 down takes us right to there. And there's the second vector. So the result, again, you can just read it from your graph. It's 3 on the real axis, and on the imaginary axis, it's minus 3. So subtract 3j, don't forget your j, and there's your result. So that's how you would subtract complex numbers using this method. Now again, obviously, this is not the most efficient way to do it. In fact, if you were just told to subtract two complex numbers on a test or on a quiz, you're much better off just using the technique we saw in our last video on basic operations. So I would really call this 5 minus 2j, and I would distribute the minus sign inside the second brackets. So minus 2 minus j, and now you combine your like terms. 5 subtract 2 is a 3, and negative 2j minus j is negative 3j. You can see we get the same answer. All right, this result and this result are the same, but algebraically, I think it's much more straightforward, much easier. But now, at least you've seen this technique. If you are ever asked to do it again, you have seen it. All right, so now there's some practice questions after that. on page 10 and also on page 11, I believe. Yep. So you can try these and see how they work out, see how you get them. And I'll leave that at that. So when we come back in our next video, we're actually going to be looking at another way that you can write complex numbers called polar form. But understanding polar form really depends on how well you understand the concept of graphing a complex number on a set of real and imaginary axes. Okay, so we'll finish off there, and I will see you in our next video. Bye-bye.